Hello, and welcome to today's 60-minute webinar, Advanced Motor and Drive Analysis. I'm Lisa Arrigo with SAE Media Group, the moderator for this program. Our speaker is Dan Kasemis, General Manager of North America at Yokogawa Test and Measurement. Dan is going to talk to us about how to get past ground-level measurements and delve into comprehensive solutions that leverage test and measurement instruments, including power analyzers, high-speed data acquisition, and real-time software. After Dan's presentation, we'll have a Q&A. If you have questions, please send them at any time through the Ask a Question box. If you would like a PDF of the slides, you'll find one under Event Resources on your screen. And now, please welcome Dan Kasemis.
Thank you. Well, first I'm going to introduce a little bit about Yokogawa Test and Measurement. Yokogawa Test and Measurement is part of Yokogawa Electric Company, which was founded in 1915. We have 18,000 employees in over 50 countries with an annual revenue of around $4 billion. Yokogawa Corporation of America was established in 1957, and our Test and Measurement divisional headquarters is in Atlanta, Georgia. Today, our agenda is Advanced Motor and Drive Analysis. We're going to look at the electrical inputs to a motor and the mechanical outputs. We're going to talk a little bit about modeling of electric machines and motors and electric control of electric machines. And then we're going to show some of the relevant measurements that we can make with modern test and measurement systems. I also want to take a moment to mention our previous webinars, since this is the Advanced Motor and Drive Analysis webinar. We also have one that kind of precedes this, which is our Motor and Drive Analysis webinar, where we deal with multi-phase power measurements, power analyzer wiring, and avoiding a lot of the common pitfalls around power measurements with motors and drives. We also have a webinar on the fundamentals of power measurement, which is kind of a Power 101, which is a very good base level, establishes a nice base level for power understanding. And then we have a webinar on harmonic distortion and measurements on distorted waveforms, which is also relevant to motor and drive analysis. So all three of these do tie into our topic today. But today, we're going to focus on the controls and the machines themselves. We're going to kind of look at what these controllers are actually doing, so we can change our perspective on how modern instruments can be leveraged to make some of these unique measurements. So let's start with a discussion of electrical inputs and mechanical outputs of the motor. Just a caveat here, we're also going to talk a lot about how torque production occurs. That's kind of what we're going to focus on because a lot of motor control applications are really torque focused. So the mechanical outputs, let me start out with the electrical inputs to the motor. If we look at point 4 in our diagram here, the key measurements we're going to be making are typically around voltage, current, frequency, and power. And again, these are the electrical inputs at point 4 of our diagram on the right. If we look at the mechanical outputs of the motor, we're typically looking at speed, torque, power, and also rotary position of the output of the motor. So just a quick refresher on what's actually happening here between the inverter and motor interaction. So the inverter is responsible for developing a rotating electromagnetic field in the stator coils of the motor. This is so the rotor, so the blue circular arrow here on the right-hand side, chases the yellow arrow around in a circle. This generates, obviously, a mechanical motion at the output of the shaft of the motor. So the mechanical speed of the motor is proportional to electrical frequency. So if we look at the inverter output stage and how it's developing the magnetic field inside of the stator, one way to think about it is that the inverter is generating an output voltage in service of developing current in the stator. That is, in order to have current in the coil, it needs to have a voltage developed across it. So if we can examine the inverter's electronics, we can see it's made up of 6 switches. In this case, in this particular case, therefore, the way it generates a specific small voltage in small time slices, that's the blue trace there. The inductance of the motor smooths this voltage out into a sinusoidal wave shape, which is shown in the red trace, and the frequency of this red waveform is proportional to the speed of the motor. And the frequency of the short pulses in blue is called the switching frequency. Again, the blue switching frequency is in service of building small increments of voltage in the stator coil to develop this sinusoidal current. Now, just a caveat here, I want to note that we're assuming a sine wave type of commutation, and these wave shapes can be significantly different based upon the commutation scheme that's used, but the general ideas are the same. And for the most part of this presentation, I'll be talking as if I'm assuming the motoring mode, so we're driving the motor rather than a motor generator unit where we're also in regen, but the concepts still apply. So to be more specific about the fundamental frequency setting the rotor speed, we do need to mention the motor types. In a synchronous motor, the rotor speed is directly proportional to the fundamental of the frequency of the current. Typically, a synchronous machine will have a permanent magnet in the rotor. And one way to think about it is, again, the inverter generates the field for these magnets to chase the motor. and therefore, the motor speed is locked to this fundamental frequency. In other words, it's synchronous. And the equation for this is shown below. In an AC induction motor, it's a bit different in that we won't have permanent magnets inside the rotor. It's actually got another set of coils in the rotor, and the rotor is not perfectly locked to the speed of the rotating magnetic field in the stator. The rotating magnetic field in the stator is still called the synchronous speed, but the difference between the rotor speed and the synchronous speed is called slip. And this amount of slip typically varies with the load applied to the motor, and the equations for synchronous speed and slip are shown here below. So let's talk about torque production. Mechanical torque is set by the electrical current. So again, if we think about the inverter's voltage to be in service of generating current, the current can be thought of as being in service of generating torque production. So to have a torque, we need a current. To have a current, we need a voltage. The magnitude of these currents in the fundamental waveform, again, the red waveform, is responsible for torque production at the output of the motor. One of the key measurements for a motor and drive system is to understand how efficiently we're performing work. Power is actually work performed over time. For electrical power, the simple equation is roughly voltage times current. However, we need a bit more nuance when we're dealing with complex wave shapes, like our switching waveform in the blue and our sine wave current shown in the red. So we use this equation, which is instantaneous voltage times instantaneous current integrated over some period in time times 1 over t. Typically, that big T is a function of or is set by the fundamental frequency in red. A power line cycle, it's often called, and we're usually averaging over a couple of power line cycles. Or I shouldn't really say power line in this case, but fundamental frequency cycles. For the mechanical part of the system, it's quite a bit easier. The equation above applies for speed and torque. And the signals there at the output are typically DC, relatively speaking, shown at the right. I'm actually going to show some measurements, some AC measurements later on at that point. But mechanical power tends to be quite more simple to measure than electrical power. Okay, so let's discuss the key measurement of efficiency. Now, I chose to show two equations here, which is somewhat dangerous, but I do believe they're relevant for this given audience. The top equation is very simple. It's everything that's coming out of the motor that's divided by everything that's going into the motor, right? So our mechanical output of the motor on top divided by our electrical power input on the bottom. The equation on the bottom, and I put some notes there on the right-hand side, includes the fundamental frequency, which is the torque producing component, the switching frequency, and all of the harmonics that result from those two signals. The bottom equation has a caveat. In this case, we're going to show a best case scenario by isolating only the power delivered by the fundamental frequency itself, aka the torque producing components. Modern power analyzers have this capability through the use of real-time FFT transforms that pull out only the power delivered at a given frequency, or even specific harmonics of that frequency. And the reason I'm showing this is we oftentimes get calls from customers where there is a bit of discrepancy between what a physics model or mathematical model may have predicted in terms of efficiency performance versus what actual performance is. And one way is to sanity check this by doing a theoretical best case scenario efficiency measurement. The reason this is also so useful to do is if we suspect there's radiated or conducted EMI in the measurement system, it's often more likely to occur at higher frequencies. And so when we isolate the fundamental, we avoid this. However, again, and I said there's a caveat, it's probably not the best case to be using it as a regular practice, because if you do use this, you're going to be essentially ignoring the potential losses in the system that are not delivered around the fundamental frequency. So again, the components of the switching frequency or the harmonics of the fundamental frequency will be ignored. If anything, it can be useful to measure both of these measurements simultaneously with a really good power analyzer. So now that we've examined the output of the controller, now that we've examined the output of the controller and the motor, let's have a look at what's going on inside of the controller itself and why. We're going to touch briefly on field-oriented control, which is not the only method for control, but it's very popular in higher-end applications, as we see in the transportation industry. We're going to touch on electric machine or motor types and why they tend to be controlled a certain way. And we're going to be showing some actual measurements. So let's briefly talk about field-oriented control. It's a method for controlling a multi-phase system with pairs of orthogonal vector components. A very generic way of saying it is, it's what's happening inside the black box that is the motor controller. Basically what we're doing is we're controlling a multi-phase motor by applying a DC control model at the input of a complex AC commutation output. And I'll show you a diagram that will make more sense of that. It only requires us to use a PID control on two target variables that are a function of what's called the direct axis and the quadrature axis. This allows us to do direct torque control, which accommodates multiple machines types, which I'll also touch on. And it also allows us to expand the operating speeds of a motor through field weakening. It's typically used when performance matters over cost and precise, smooth torque control is required. I mentioned, briefly mentioned earlier, other commutation techniques, stepping or trapezoidal control are some of those other techniques. So in a huge oversimplification, I'm going to say that field-oriented control allows a multi-phase AC machine to be controlled like a DC machine. This is often called transferring from the stator reference frame to the rotor reference frame by leveraging some math models of the machine itself. And I've got a diagram of the two models below. So again, we're converting the three-phase stator view into a pair of coordinates on a DC axis, which are called the direct and quadrature axis. So let's look at this controller inside an example controller and see how this works in a step-by-step manner. I'm not necessarily going to go into the how or why specifically of the math. We don't really have time for that, but we'll do our best here to walk you through an example. So if we look at the blue number 1 here at the input to our motor controller, there's typically some type of target torque produced. For example, in a vehicle, it might be a pedal press establishes a torque target for us. This may go through a model or a lookup table in a microcontroller to convert torque demand to 2 ID and IQ target currents. So that's point 1 at the input of our controller. If we jump to the blue part on the right-hand side, the blue number 2, the next step is we measure the rotor position of the motor, and then we measure the three-phase A, B, and C currents. In step 3, the next block to the left, we convert those three-phase currents to a two-phase system, I alpha and I beta. We do this using something called the Clark transform. In step 4, we then take those two-phase components and use the Clark transform and convert these to DC values of ID and IQ. That's right there underneath the number 5 on the diagram. So what's important to remember here is those are actually measured ID and IQ now. If we walk from step 4 up to point 1, step 5, step 4 to point 1, we're comparing our target values of ID and IQ to our measured values of ID and IQ. We're coming up with an error measurement, right, which is common to PID controllers. Here we're really using a PI controller. Once we do this, we can produce a VD and VQ value, right? So those are voltage values because remember I said earlier that we're generating a voltage across the coils in order to develop a current. So those are our targets. In step 6, we take those two VD and VQ values and we do an inverse Clark transform to create a two-phase system. And then in step 7, you can use the inverse Clark to create a three-phase system and then a PWM scheme, which we see on the right-hand side, the pulse width modulation output. Or there's some other methods here, such as switch vector pulse width modulation that we can use that actually kind of skips the inverse Clark transform. So there I've walked through kind of one iteration. One thing to remember is all this is happening inside that black box at a very high rate continuously. So now that we know what the controller is doing, let's have a look at how some of the synchronous machines themselves work in terms of torque production so that we can make sense of why current control is so important. On the left-hand side, we have what's called a permanent magnet surface-mounted machine. That means that the magnets on the rotor are mounted on the outside. Looking at the equation below, you can see torque production comes from the flux linkage constant, and which is in Webers, and the quadrature current of IQ. On the right-hand side, we have a interior permanent magnet mounted machine where the magnets are on the inside of the rotor material. Looking at the equation for torque, you can see that we have two sources now. One comes from the flux linkage constant of the motor times IQ, plus we have the reluctance torque, including ID and IQ, and this torque comes from the reluctance path that exists in between the magnets, and you can see that on the purple arrows I've denoted there. So two different motors, two different methods for developing torque. So we can see from these equations that torque production is highly dependent upon the direct and quadrature components of current. We can measure these components by understanding the angular displacement of the stator current and the rotor position with respect to the direct or quadrature axis. This measurement is often called the load angle. So if we extract the fundamental frequency of the stator current and we measure the load angle, we can compute the direct and quadrature currents using some simple trigonometry. And I've put these equations on the left-hand side underneath the XY drawing there. So on the right-hand side, if we look at the case of the surface-mounted motor, we can see the best case for efficient torque production, which is often referred to as the maximum torque per amp, is when the load angle is at 0. So all of the torque is produced by IQ and the flux linkage constant from the magnets of the rotor. If we examine the motor below the internal permanent magnet mounted motor, we can see the best case for efficient torque production is going to be when we take advantage of the torque produced by the combination of the flux linkage constant times IQ and the reluctance torque, which includes, again, both the ID and IQ currents. This means our maximum torque per amp or best case torque per amp production is not at a load angle of 0. Perhaps it's somewhere between 5 and 45 degrees. Largely, this is going to depend upon the design geometry of the rotor and also depend upon the speed and load points you're operating at. Okay, I've talked about controllers, I've talked about motors. Let's look at some real-world measurements. So I've got a diagram here, and this is really just to illustrate what we might see for typical needs in a motor dynamometer type setup. You'll typically have a dynamometer, an electric machine or a motor device under test with a controller. We've talked about those two components. And one thing that's important to remember is this system gets pretty complex really fast, in that we have two closed loop controllers here to look after. One that is operating the dyno itself, the load side on the diagram, and one that is inside your controller, like we discussed. We also typically have, in this case, we have a drawing where we've got at point 1, we've got an AC input, for example. We will typically have maybe a power source for that. If you're doing DC input, which is typical in the transportation industry, we're going to start really past the AC to DC stage. So we're going to start at point 2. There you're going to have a DC power source, a battery simulator, something to simulate typically your battery pack that you might have in a vehicle. When we talk about instrumentation required, on the right-hand side, I've got points 1 through 4 pointed out there. We're typically making a voltage measurement. That voltage measurement has to have high accuracy, high sample rate, typically a bandwidth that is higher than our switching frequency we talked about. We want it to have high resolution as well as some filter options. When we're measuring current, we're looking at high currents, especially in the transportation industry, and those measurements should be accurate, again, for our efficiency measurements. Oftentimes, we'll see the CAN bus. That's a communications method, commonly used, again, in the transportation industry and other industries to get signals out of our inverter. Frequency is an important measurement. It's not often talked about, But as we examined in the first part of our webinar here, we want to decouple the fundamental frequency with real-time FFTs in our pulse width modulated waveforms. And we also want to do some analysis typically on the pulse width modulation schemes themselves. So at points 4 through point M, we're largely talking about the mechanical output of the motor here. We're measuring the torque, we're measuring speed, we're measuring rotor position, and there's multiple ways to do that. There's usually an analog type output for torque, maybe a frequency or pulse type output for torque. For speed, typically we're dealing with a frequency measurement for speed given by a rotating sensing device such as a encoder or maybe a resolver. And we're going to be measuring our electrical power at point 4, and we're going to be measuring our mechanical power at point 5. So this is a typical setup. For the experiment I'm showing today, this was our actual setup. So this is one of our test benches we have. We're using a programmable inverter. We're using a motor that was actually unknown to me. We're using a hysteresis brake dynamometer, in-line torque sensors, speed sensors, an encoder for position. And for instrumentation, we have the Yokogawa DL950 scope quarter, the WT5000 power analyzer, and IS8000 PC software to integrate all of these measurements together for real-time viewing, configuration, recording, and analysis of these signals. So let's actually look at some measurements. If we're running our motor at a steady state load and speed, we can examine the speeds of the electrical signals we talked about earlier. So using the scope quarter to do a 50 million sample per second capture on a couple of revolutions of our motor, we can look at the output stage and see that we have a switching frequency, and that's the yellow trace. The top yellow trace is our line-to-line voltage. We have a switching frequency of 16 kilohertz. We can see the current trace, there's our sine wave, the blue trace, overlaid with the real-time rotor position, which is in orange. That comes from our encoder. What we can see is that we have 5 cycles of the fundamental frequency, right? That's the speed, the electrical speed of the motor, for every 1 revolution, mechanical revolution of the rotor. That's the orange ramp that's going from 0 to 360 degrees. So if we run our math we previously covered, you can see the measurements of the fundamental frequency and the mechanical frequency equate to a speed of approximately 200 RPM. Zooming into a very small section of the PWM. I'm sorry, Lisa, are you there? I'm getting a message that I've disconnected.
Okay, we're on slide 26. Would you like me to move to slide 27?
Yes. So I'm not showing. You're not seeing slide 27 now, correct?
No, I've just advanced slide 27 to the audience.
Okay, great. Thank you. If we zoom into a very small section of the voltage and current waveforms, we can examine some of the PWM characteristics. Looking at the blue trace, we can see the PWM ripple current, the switching times, their frequencies, the average magnitudes of the high and low. So let's look at the peak-to-peak ripple current on our PWM signal. You can see it's 455 milliamps at 15 kilohertz, roughly 16 kilohertz. Our switch times, our positive width switch times, 19 milliseconds and 43 milliseconds for a total of microseconds, for a total of 62 microseconds at 16 kilohertz. The average high magnitude of the signal, so this isn't the peak, this is the average high magnitude, is 2.14 amps, and the average low is 1.95 amps. And again, we're looking at, in the upper right-hand diagram, I put a yellow rectangle around the PWM stage that we're examining in the controller. So next slide, please. We can also use a special feature of the scope quarter that allows you to input the switching frequency, and a real-time DSP channel will compute the actual voltage occurring for every little pulse width. Remember I talked about the small increments of voltage we're developing for a given signal. In this display here, the red trace shows the voltage delivered by each tiny pulse width of the yellow trace. Again, the yellow trace is line-to-line voltage. This can be used to investigate the PWM output stage and tell you exactly what voltage you're delivering for each little time slice of the PWM. Next slide, please. So, using the same feature again, we can change our connection points. And in this case, I connected my ground point to a DC ground point in the system. Probably could have used a star point as well, but still, I got the desired result in the red trace. We can see that there's a technique here being used, a modulation technique, that takes advantage of the third harmonic. This is typically done to increase the output voltage of an inverter by about 15% over a conventional sine wave pulse width modulation technique. What's interesting is in our last slide, this third harmonic did not show up when we're connected line to line. And that's because the harmonics, the third harmonics actually cancel each other out when you're looking at things that way. On the right-hand side, I showed a little simulation diagram of third harmonic injection. There's a couple different techniques here that can be used. So switch vector PWM typically uses more of a triangle wave for third harmonic injection. And then there's also third harmonic pulse width modulation. So next slide, please, Lisa. Earlier, I had shown a ramp wave of the rotor position. Let me show you how we got that. We were using another real-time math function where we took the A, B, and Z signals out of our rotary encoder, and our real-time DSP channel is producing the orange trace, which is the real-time rotor position. On a third channel, we used another feature, or we were able to use another feature that will take the torque sensor output and convert it to units of Newton meters. This is often, again, an analog or frequency type signal. So we've got our rotor position in orange and our torque in red. Next slide, please. So we can make some interesting observations with this information now on our torque signal. In this case, you can see the red trace is really stair-steppy and a little bit ugly. And I actually chose to keep this in just as an example of a potential gotcha. Oftentimes, you'll get your torque trace out of a signal conditioner or another system where it might be conditioned. In this case, I was getting the torque trace from our dynamometer controller, which has a D to A repeater in it. And you can see you've got this stair-steppy response. It's not necessarily desirable, but I chose to leave it in. And you can see here also our current trace in the blue just below. We've done a 100 million sample per second scope quarter capture here, and we can investigate the AC signals that are riding on top of this DC torque trace. So if we look at the measurements, we can see that we have a peak-to-peak torque production of 117 millinewton meters, and this is often called torque ripple, and we can see the frequency of this matches the frequency, the fundamental frequency of the machine. Now, I will, again, hang another caveat here. I purposely took this measurement at an exceptionally bad performance point for the motor itself. And I probably didn't have my dynamometer tuned the best in terms of PID, but it did a good job of illustrating my point. This motor is also, again, it was an unknown motor to me. We found out later this motor is trapezoidally wound. So that means that the back EMF doesn't line up perfectly with the sinusoidal computation, which can be a source for torque ripple. Next slide, please. We should be on slide 32 here. Another thing we can do is look at this AC torque ripple on an XY chart along with our rotor position. And in the upper left-hand side, you can see that I've isolated one rotation of the motor, and we have 5 peaks and troughs, where we have a peak torque of 667 milliNewton meters at 205 degrees. So I've used a little cursor to isolate the peak in one rotation. So we can actually isolate where some of the peaks might occur or troughs might occur over periods of rotations. And what might be interesting is to overlay multiple rotations and develop a history to see if these peaks or troughs consistently occur at a specific point of rotation. Next slide, please. Okay, so we've looked at some of the more dynamic speed signals up to this point. What I want to do is I want to zoom out and have a look at the case of my unknown motor. I do have some reason to believe that it's an interior permanent magnet mount motor. So what we did was we decided to sweep the load angle and measure the corresponding torque and torque per amp production, as well as the ID and IQ values that we measure with our power analyzer. We correlate the reported values from the inverter itself, who's broadcasting those measured values over the CAN bus using our scope quarter. Next slide, please. So what you're looking at here is a display from our IS8000 software that has collected this data from our instruments. We're measuring the RMS current of all 3 phases. We're measuring the load angle and computing the ID and IQ values from them. We have overlaid the CAN bus measurements for ID and IQ from the inverter compared to our measured values with our power analyzer. We're measuring torque from our dyno controller and computing a real-time torque per amp with our power analyzer. And we're monitoring the desired load angle from the inverter. This load angle is desired, it's not measured, so there is a difference. And then you can see our measured load angle by our power analyzer there in blue. Dyno's holding a steady state speed of about 200 RPM, and we swept the load angle to about 35 degrees while trying to hold a relatively flat stator current. So again, just to run down the signals here, the trace in red, if you can see it, is our RMS stator current. The light green is our ID, our measured ID value with our power analyzer. The dark green is our ID measured from our inverter that's transmitted over CAN bus, and they overlay pretty well. The dark purple is our measured IQ. The lighter purple is our measured IQ over CAN from our inverter. The purple trace is our measured torque, and the blue trace is our torque per amp computation, the light blue. And the darker blue is our measured load angle, and the orange is our commanded load angle. On the upper right-hand side, you can see the XY plot of ID and IQ measurements. And you can see the sweep we took, starting from the right-hand side, moving over to the left-hand side about 35 degrees, and then moving back. Next slide, please. So you can see at the bottom of the graph, we're sweeping the load angle in a ramp up, ramp down pattern, and the resulting ID and IQ plots are on the XY, and they're shown at the top. We can see for this operating point of speed and voltage, the best torque per amp production is occurring about, we'll say 11 degrees and 13 degrees load angle. And we can see past that point, torque per amp rolls off, bottoming off at the highest load angle around 35 degrees. So this does suggest to us that we have some both torque production from the interaction of our flux linkage and IQ, as well as some reluctance torque production that happens at maybe 11 to 13 degrees. So this is suggesting that we have a salient internal permanent magnet motor that's contributing to at least some of the torque production output. Note again, this is a completely unknown motor to us, and we're definitely operating at a pretty low voltage and low speed point. But part of the reason I thought this experiment was so relevant is we have many customers doing this type of work with either new systems they're developing or systems that they're reverse engineering. So let's look at some of the next steps and measurements we could make moving forward. So what we did, well, let me review what we did and then talk about next steps. Sorry, next slide. What we did was we measured the switching frequency, the fundamental frequency. We figured out the number of poles in our motor. We looked at PWM ripple and we looked at torque ripple. We decided that this was an interior permanent magnet motor with some reluctance torque contribution. Again, we weren't operating at the best point for this motor, mostly because I was voltage limited. But what we could do next is do some sweeps at various load points, different speeds, higher voltages, and the optimum load angle is likely to vary so that you've got a map. And that's what a lot of customers do, is they're developing a map of this. We could do some motor parameter identification, which is a method for determining what kind of motor do you have, right? We could spin it, get the back EMF profile, determine the flux linkage values, compute the LD and LQ values. So those would be next steps to confirm our suspicions on this motor. We could definitely do some PID tuning, and I put that in there because in these setups, we oftentimes get calls from customers stating they're getting some noisy or nasty readings, and it's actually a really complex problem because you have a couple of PID loops running, one in the dyno, one in the inverter, and that can manifest itself in different ways. So we can also do some efficiency mapping and torque versus speed plots. We didn't talk or give an example of field weakening, which I mentioned is one of the drivers behind field-oriented control to kind of increase the operating speed of your motor. And then we can also do some harmonic analysis to isolate some of the consumers of maybe waste power in the system. On the DC side, we can look at the inverter output, and we could also do harmonic analysis of our torque production. Next slide, please. So one thing I didn't cover is how to actually set up your instruments to do these measurements. I kind of just showed the measurements themselves. Here's some resources for you to look at, application notes. We've got on our website 7 steps for successful power measurements, making measurements for field-oriented control, how to make successful harmonic measurements. And these application notes are somewhat instrument specific. Some pertain to power analyzers, as well as scope quarters. You can actually do quite a bit with field-oriented control on our scope quarter platform as well. But again, we tied it all together with our IS8000 software today to give a more cohesive solution of scope quarter power analyzer, systems level view of collecting everything in one place. Okay, next slide, please. I think we're ready for Q&A.
Excellent. Thank you, Dan. That was a terrific presentation. Yes, let's take a look at questions, but first I would like to mention that this webinar will be archived and available for viewing on our website. An email will be sent to everyone who registered for today's program as soon as the archive is ready. Also, when today's webinar is over, a survey will pop up on everyone's screen. Please tell us what you thought of our webinar by answering just 3 questions. Lastly, if you would like a PDF of Dan's slides, you'll find one under Event Resources on your screen. And now for some questions. Dan, you showed an encoder in your diagram. Can Yokogawa instruments support resolvers for position?
Thank you. That's a great question. Yes, resolvers are very common, especially in more rugged automotive environments. We can support them on our scope quarter platform. However, I will say resolvers can be very touchy depending upon how you're measuring or where you're measuring from. So specifically, if you're measuring tapping into the resolver signals that are already used by the motor controller itself, those signals can be very sensitive to external probing, and it actually oftentimes can depend upon the type of chip that's used inside of the controller. For that reason, oftentimes, if we can, we recommend on your dyno to get a really high quality encoder device to use specifically for instrumentation. There's some other limitations on resolvers that encoders don't necessarily have in terms of speed and accuracy as well.
Thanks, Dan. Would you please explain how the direct and quadrature components are measured by each instrument, or is that done post-process in software?
That's another great question. So we measure these, and I say measure, but they're really computed values. In this webinar, we measured and computed them in real time in our Power Analyzer platform. Power Analyzer does this using the encoder position. We can also do this in the scope quarter platform. The scope quarter is a little bit more flexible in terms of programmability, but the scope quarter is quite good at doing it at really high speeds for, again, more dynamic analysis. We don't do it in post-process in our software. We really offload that to the hardware.
Very good. Thanks, Dan. Next question. Your traces on the slow speed data look a bit noisy. Do you know why that is?
Yes. This actually, I mentioned it a couple of times. I was working in a load range for this motor that was pretty low efficiency, and I know that because I made some efficiency measurements. And given that range, we also had to do a lot of tuning of the PID control for the dynamometer, which might have been a little bit oversized. But again, I think that's a great question because it is something that comes up from our customers. First thing that's always looked at is the instrument itself. Why is the measurement wrong? But really, you have to be careful because it's a really complex system. So we had a little bit of jaggedness on some of our measurements, and a lot of that had to do with the operating point, the dynamometer size, and the PID tuning.
Thanks, Dan. Dan, could you list maybe 2 or 3 key concepts that you hope the audience takes away from today's webinar?
Yes, I think that understanding specifically when it comes to torque control, what is going on in the motor. Oftentimes we get lost in how accurate is voltage, how accurate is your current. But I think understanding the concept of the voltage being developed in the stator in service of creating a current, in service of creating a torque, is a quite important concept. And then lastly, your instruments are often used to make raw measurements. Give me voltage, give me current. So raw ingredients, so to speak. I think there's a lot to be gained by leveraging the capability that is already included in your hardware, the hardware of your instruments. So taking those raw ingredients and passing them through a recipe. so to speak, as an analogy, which is kind of what we did today, in developing these more higher level measurements rather than just our raw voltages and currents.
Thanks, Dan. Someone in our audience wants to know, what is the programmable inverter? Is it a virtual inverter which is coded inside the ECU microprocessor?
That's a good question. I bought an off-the-shelf programmable inverter that had a scripting language. I won't mention the manufacturer, but it was built around a microcontroller platform, and then it had a scripting interface. So I kind of generically, and hopefully not too confusingly, interchange the term inverter and controller or microcontroller in this context, because that's kind of what I had. But I realized that some of those components can actually exist separately as well.
Thank you. And with that, we're at the end of our webinar. I want to thank Dan for talking with us today and providing so much excellent technical information and insight. And I'd also like to thank our audience for joining us. It's been a great discussion. Thanks, everyone.